Hello, and welcome to Lecture 3 on exponentials and logarithms. So in the last mini lecture, we introduced one type of biological function, which is a polynomial. And if you recall, polynomials show up because we often use them to fit data. Today, we're going to introduce two more types of biological functions that will be used throughout this class. The first of those is an exponential function, and the second is a logarithm. All right, so first, an exponential function is any function f of t that has the form b e to the at. So let's break that down. What is t? T is our independent variable. The quantity b here is a constant, and it is known as the base of that exponential. All right, so f of t is the independent variable, or sorry, the dependent variable. And the whole quantity AT here, the whole thing that B, the base, is raised to, is known as the exponent. All right, so it is important to distinguish between exponential functions and power functions. Power functions have the independent variable in a different place. So instead of having a base raised to the independent variable, we have the independent variable raised to some constant power. So one place that we see this is in the terms of an exponential. So powers show up in the terms of an exponential, whereas the independent variable is in the exponent of an exponential function. All right, so some examples of exponential functions include y equals f of x equals 2.1 to the x. So note that this base b can be any real number. So it could be 2.1, it could be 3.141592, etc., etc. It could be lots of different quantities. All right, um, and the independent variable that we have can be t, and it can be x, or it could be any other letter. So here we have the independent variable x. All right, so in this class, two specific bases are going to show up again and again. The first of these is known as the common base, or base 10. So we have f of t is equal to 10 to the t. And we also have a base that's called the natural base, where f of t is equal to e to the t. Now, e is kind of like pi. It's a special number that goes on and on and on. It's an irrational number. It never ends. We could write decimal places forever and ever, and we would never get to the end of those decimal places. And in particular, these decimals are given by e equals 2.7071, etc. All right. So there are some people that are crazy enough to know the first 100 terms of E, just like people know the first numbers of pi. All right. But these two are going to come up again and again, where we have base E and base 10. All right. So just like you need to know the shape of a polynomial, you should be able to recognize the shape of an exponential function. To do so, we can think about some particular characteristics of an exponential. The first of these is that it has the domain of the real numbers. So it can range anywhere from minus infinity to positive infinity. How do we write that in set notation? Remember, we use an open bracket because we can never get to minus infinity, and we can never quite get to infinity, so we write those with open brackets. All right, the range of the exponential function is the positive real numbers. It can be any real number, but it can't drop below 0. In particular, this is described by something called a horizontal asymptote. So we get closer and closer and closer to 0, but we never quite get there. As a result of the horizontal asymptote, there are no roots. So we never cross the x-axis, and so therefore we do not have any roots. However, we do have a y-intercept that is always at 1. So that gives you the shape of an exponential. In order to deal with exponentials, we have a few rules. First, if you have two exponentials multiplied by one another, this should be an A, not a B, uh, then you can add their exponents. So if you have a to the r times a to the s, then you have a r to the s. One way of thinking about this is to actually put in a value for what a is and r and s are to understand this. So suppose we had a squared times a cubed. One way of writing this would be a times a times a times a times a. This is our a cubed. This is our a squared. So we end up with 5a's, which is the sum of the 2 and the 3. All right. Similarly, if we have a to the r over a to the s, then we have to subtract their exponents. So this is given by this example over here, where we have 2 to the 3 divided by 2 to the 5. Once again, you can write this out where you have 2 times 2 times 2 divided by 5 2's. 3 of those 2's are going to cancel on the top and the bottom, and we end up with 1 over 2 times 2, which is equal to 1 over 4. All right. Similarly, if we have ab to the r, then we can distribute that exponent r between a and b. So one way of thinking about that is 16 to the 1/2. Remember that if we have a fractional exponent, that this is the same thing as having a root. So in particular, if we have something to the 1/2, that is the same thing as a square root. So the first thing we can do is we can distribute that 1/2. So we have 16 to the 1/2 and x to the 1/2. Another way of writing that is 16, square root of 16 times the square root of x. We can actually know what the square root of 16 is. 16 is 4 times 4, so it can come out of the square root by just being a 4. All right. Similarly, if we have a over b to the r, you can distribute that r just as well in a product as you can in a quotient. All right, so if we distribute our 4 exponent of 4 in this case, we have 6 to the 4th over x to the 4th. I just want to remind you that if you have something in the denominator that is raised to the power, you can move it into the numerator by making that power negative. All right. So there's another detail to how the shape of exponentials, and that is the sign of the exponent. So in particular, in the previous example, we talked about e to the t or 10 to the t, and all of these have exponents that are positive. But that exponent doesn't necessarily have to be positive, and that is going to distinguish between exponential growth and exponential decay. All right, so for example, consider the function e to the ax. If a is equal to 1, then we have e to the 1 times x, that is positive, and this is going to lead to exponential growth. So once again, we have a y-intercept of 1, and then our function grows from there. In the case where we have a equals -1, then we have e to the minus x, and this leads to exponential decay from our y-intercept of 1 and a decay towards 0. Remember, it does not cross the x-axis. It just gets closer and closer and closer to this horizontal asymptote. All right. So that is exponentials. The second function that we're going to be talking about is logarithms. The logarithm is any sort of function f of x that has the form log subscript b. The b here is known as the base of the logarithm. And then we have the argument of the logarithm, which includes our independent variable x. All right. So if we want to understand how to read a logarithm, they're kind of confusing functions. One way we can think about it is you take your b and you ask, if I take b and I raise it to y, what value of x does does that give me? So b to the y is equal to x. So think about going around in the circle. The base to what dependent variable is equal to the independent variable. So I often find that as an easier way of interpreting a logarithm than as simply as a logarithm. All right. So here are two examples of a logarithm. We have y equals log base 2 of x. What is this saying? It's saying that 2 to the y is equal to x. And similarly, we can have something that has a rational or irrational number as the base. And so we could have 3.14 raised to the y is equal to 5x. All right. Just like with exponentials, there's going to be two particular bases that we're going to find useful in this class. The first of those is the common base, which leads to the common logarithm. And we also have the natural base, which leads to the natural logarithm. These are the same bases as we have in exponentials. So we have base 10 and base e. They're so common that we even abbreviate them. So if we have base 10, we just drop the 10 and we just write that as log of x. If we use log of e, then we write this as the natural logarithm, which some people know as the ln of t. Okay, so just like with exponentials, you should be able to recognize the shape of a logarithm. In some ways, it looks like an exponential turned on its side, and that is not, that is actually very true. So just like the exponential, we should be able to recognize its domain and range. The domain of a logarithm is the positive real numbers. So we have a vertical asymptote here. Where we get closer and closer and closer to the y-axis, but we never quite reach there. So this means that there is no y-intercept. This is important to realize that you cannot plug a negative number into a logarithm. So you cannot have log of -3, for example. This does not work. You have to have a positive argument of your logarithm. Similarly, we have an intersection here, a root of 1. So just like the exponential has a y-intercept of 1, now we have a root of 1. And the range of the logarithm, so the values on the y-axis it can take on, are everything from -infinity to positive infinity. Just like we have for exponentials, we have some rules for manipulating logarithms that are going to be helpful. The first of these is different between exponentials and logarithms, and that is known as the change of base. So we didn't have a change of base for an exponential, but we do for a logarithm. So oftentimes we aren't going to be happy with the base a that we have, and so we want to turn it into a base b. And in order to do this, we move the base that we want into the denominator, and we have the base that we have. Oh, sorry, that's backwards. So if we want to change from a base b into a base a, so you have log b of x, you take the base b that you have and you move it into the denominator, and you take the base that you want and you write it as the new base. The argument stays in the numerator. Okay, so for example, we might have log base 2 of x, and it might be inconvenient to have log base 2. Instead, we might want to write that as something, one of the common ones that we have. So, for example, the natural log. So we're going to take this 2 and write it in the denominator. And we're going to have x, and we're going to put that in the numerator. This is now log base e of x divided by log base e of 2. So we now have our log base 2 of x written in terms of two logarithms with a new base that we like, which is the base e. All right, some other logarithm rules are if you have the log of a product, then you can write that as the sum of the logs. So log base b of x times y is equal to the log base b of x plus the log base b of y. So here is an example of that applied in practice. If you have the ratio or the quotient of x and y, just like you would have turned a product into a plus sign, you're going to turn a quotient into a minus sign. So this quotient becomes log base b of x minus log base b of y. Finally, we have a really nice rule that if you have log base b of x to the r, this r can move out front, so we can take exponents out of logarithms to end up being a product. So we have r times log base b of x. So in one example, if we have the natural log of x squared, this is equivalent to 2 times the natural log of x. Why does this make sense? Well, we have that we could have ln of x squared. Another way of writing this is ln of x times x. We know here that if we have a product, we can write that as a sum. So this is equal to the natural log of x plus the natural log of x. And so we could simplify this to just simply have 2 times the natural log of x. All right. So an important property you might have noticed is that a lot of the things in a logarithm were exactly opposite of an exponential. And this is not just your imagination. It is in fact because exponentials and logarithms are known as inverse functions. So an exponential undoes a logarithm, and a logarithm undoes a natural log. Or a logarithm undoes an exponential. So E undoes ln, and 10 to the power undoes the common log. So, for example, the natural log of e to the x, the ln and the e can kind of cancel, and we end up with x. And if we have the common log of an argument of 10 to the x, the log and the 10 cancel, and we just end up with x. All right. Similarly, we can go in the other way. We can raise a natural log. We can take e to a natural log to cancel the e and the natural log, and this will just give us x. And we can take our common log and we can raise that to a power 10 to have the 10 and the log cancel, and we end up with x. Why do we care so much about inverse functions? Well, they help us solve equations. So suppose we want to solve the function y equals a to the x for x. How do we do this? Well, we want to isolate this x. Remember what you're trying to do. You're trying to get that x by itself. Right now it has a to the x. So how do we get rid of that a? Well, we can take the log base a of both sides to get rid of it. So we can have the log base a of y is equal to the log base a of a to the x. This lets us cancel the log base a and the a, so we end up simply with the log base a of y is equal to x. And now we have solved that equation by using the inverse properties of e and the natural log. All right. So similarly, we could try to do use the opposite of the inverses to find the x in this equation here. So we have a log base a of x, and we're trying to isolate that x. So let's raise both sides to the a. So we have a to the y is equal to a log base a of x. Since I have the a and the log base a right next to each other, those two can cancel, and I just have that x is equal to a to the y. Okay, a final example. Suppose we're trying to isolate x. In this case, well, there's two options that we have. The first option is that we could recognize that this is a logarithm, a log base 2. So option 1 is we can recognize that this is log base 2, and we can raise both sides to the 2. So we have 2 to the y is equal to 2 to the log base 2 of 8 to the x. Now, the 2 and the log base 2 cancel, so that we only have the argument left. And then we could take the 8th root of both sides to isolate that x. Okay, so that's a little bit cumbersome and not particularly very nice. So instead, let's take option 2 and recognize that we can use our logarithm rules, and this is an exponent. The x is an exponent, so we can move it down. So we have y is equal to x log base 2 of 8, and then we can simply divide both sides by log base 2 of 8 to get x. All right, so there are your, this is a much simpler derivation that uses our logarithm rules. All right. So with that, I'm going to leave you with the self-study question that is going to use the logarithm and exponential rules to solve functions, and I'll see you in class.